Well, this is summarized in this video. The problem is the curve is given by r of t, and I use here the bracket notation to represent moving away from the I component, J component, K. It works out better. And the reason is because it's easier to do inner product. Okay, so RT is given by this, and then R prime of T, of course, is the derivative of that. And you just differentiate respect to T pointwise. And often we normalize this, so it's R prime O divided by absolute value R prime of T. Okay. Fortunately, the thing that makes this a little difficult is this involves a square root, but the work formula does kind of cleans out or eliminates this square root term, so that makes the calculation much easier. So here I have the graph of the curve from 0 to 2 pi, and it kind of looks symmetric. And no matter how you slice it, if you're going this way counterclockwise, when we loop around, we're going clockwise direction. So the work net result is, if this work here is positive, then this work is negative, and the negative will cancel the positive. So it'll be 0. So maybe the appropriate limits of integration is as I suggested, or was pi over 2. But anyway, I drew the curve from t equals 0 to 2 pi. And the force vector field, of course, is f of xy. And at the point on each point of the curve, it will be just 1 plus phi sine of t raised. So remember, it's the x, y, and z. So here's a picture of a couple force vector fields along particular points on this curve. So here's a force vector field here, point here, and probably here where the two curves intersect or loop, you see the force vector field points, let's see, in that direction. And probably it points in the opposite direction when it loops around. You just have to evaluate it. But I didn't. Now, the formula is pretty straightforward. It's appropriate limits of integration, definite integral of f dot r prime of t, which is, of course, is the dot product. So the dot product of the force vector field, which is highlighted in green, with the tangent vector field, which is in red. And if we expand out the dot product, it's the first green term times the first red term plus the second green term times the appropriate second red term, and finally plus the last term times the corresponding red last term of the tangent vector. And you sum this up, right? And then it ends up that the definite integral it breaks down easily to 6 definite integrals, where we simplify the dot product into 25 cosine sine t, and we integrate term by term. Now, there's a conjugate term in here, and the only reason is because dot product is recognized for vectors because of the bracket notation. Dot product assumes that maybe the terms are not necessarily real but complex. Anyway, but to cut right to the chase here, each of these the last 3 definite integrals are pretty straightforward. They're just with appropriate signage. Minus sign is really sine of t minus sine of t divided by 2. And this term, of course, is minus sine of 3t divided by 3. And the first 3 integrals, here are their indefinite integral. 25 cosine t sine t happens to be 25 over 2 sine of t squared. And then this one, of course, is minus 2 because you got the 2 that cancels with, actually it's a 4 square. And then this one here is going to be minus 9 over 2. Okay, now I evaluate this for pi over 2 in the first case here, and that gives me 15 for the work. And then if I evaluate from 0 to pi, it gives me 0 because already you've already made one loop around the curve, and the positive work component of the work is going to cancel with the negative. Now, for this, it's just a slight motivation of how the formula evolves from the physical interpretation of work. So the curve R, we consider R prime over T divided by its length. Absolutely. That's what we call the unit tangent vector along the curve. And a lot of times in differential geometry and differentiation, or integration or analytical geometry, we always like to look at a unit vector, whether it's a tangent or a force vector. So the component of F along the unit tangent vector field or dot product is a force that pushes the particle along the curve. And we rewrite this in terms of, here is the dot product, and then I factor out the 1 over r prime t as a scalar, the absolute value of that. And then this is the component force that is applied to the displacement, which is ds over, which of course is just arc length formula, which is absolute value r prime t dt. And then you take these incremental force, which is the dot product of this, and you pass through the limits, we get the definite integral from a to b of the dot product f prime r prime times the r absolute value r prime. And luckily for us, the denominator with the absolute value cancel with with this term, which also has the absolute value. So there is no absolute value, and that leads us to the simplified formula for the work from A to B. And here's a kind of a visual of what we're talking about. Here's a point on the curve. Here's the force vector field along here. And then this is the tangent vector, unit tangent vector field along this point. And so we have to take the component of this force vector field along this unit tangent, which is the dot product. And then that's the unit tangent vector field right here. And then the displacement is this arc length here. And that gives us these combinations here, or the ingredients in this definite integral. And then, fortunately, like I said, the absolute value of length cancels. And so that gives us a very simple formula for the work of performing along a curve. Okay, so I try to keep this as simple as possible. I hope that works. Not a lot of hemming and hawing. And if there's any questions about this, if you want me to go over some of this recalculation or the brute force definite integral, feel free to drop me a line or hook up and we'll do it. I'll be glad to do it for you. And that's it.